more minutes, please.
Sure.
Mhm. Tá, e Márcio está naquela tela branca lá ainda, é isso mesmo, né? Ainda não está ao vivo. Parece que agora está ao vivo, né, Márcio?
Ok, estamos ao vivo.
Okay. So, good afternoon, everyone. It's a pleasure to have today Alexander Khajetoorians. So Alexander obtained his PhD in physics at the University of Texas, United States. He has been a postdoc researcher at Radboud University. He has been awarded with prestigious personal grants such as the Emignator Group and ERC Consolidator Grant. And by nowadays, he is a full professor and head of the Scanning Probe Microscope Department at the Institute for Molecules and Materials at the Radboud University in the Netherlands. So, Alexander, thanks a lot for accepting our invitation. And please, the audience is yours.
All right. Thank you, Angela. First, let me say thank you for the invitation. It's also nice to meet you. Should also say that since I was a teenager and I heard my first, I don't know, Jobim album and heard the word beleza, I think going to Brazil was always a big dream of mine. I still have failed. I hope that...
I hope in the near future can come here personally. And I live at the Amazonia region, so it would be a pleasure to have you, to hold you here.
Yeah, so it would be a dream that we could have done this in person with all of that are in attendance, but I'm happy to at least consolidate that we can at least talk virtually and welcome everybody and thank you for being here. Today, I'd like to give you a little bit of an overview of what we're doing in our department, mainly related between the world of single atoms. So that's kind of the title of my talk. What can we learn from atoms? And show that we can actually mimic a seminal machine learning model called the Boltzmann machine. But this is actually tied to a very deep physical problem, which is trying to understand the regime in which we, let's say, of complexity, in which we can actually utilize physical behavior to mimic concepts like we see in machine learning. So I'm going to walk you through a little bit of that. Before I do that, let me kind of introduce you with my part of the world where I'm sitting here. Let me get the laser pointer going as well. There we go. So yeah, Radboud University, as Angela mentioned, is in Nijmegen. And we sit in this beautiful building for the Faculty of Science, where the Institute of Molecules and Materials is living. And this is the SPM department. We have a number of different people in our group working on lots of fun topics, mainly focusing traditionally on surface magnetism, but also understanding novel electronic properties and collective and many body phases of matter, such as superconductivity or topics like lower dimensionality. And our approach is mainly based on scanning probe microscopy, as the namesake is there. The department is run by a number of staff members, which I'm really lucky to work with. So Nadine Hauptmann and Daniel Wegner and I take care of the academic side, and we have two outstanding scientists that help us in the lab on a day-to-day basis, Manuel Steinweiser and Henning von Alverden. And we use these setups to look here, just some simple examples of some things we've done recently. Here, for example, we've been looking at tailored interfaces for lower dimensional superconductors and understanding how hybridization plays a role in changing the superconductivity. So, we can get at that with really, really high resolution with these tunneling setups. We've been developing new ways of doing spin imaging. That's something Nadine's been working on for the last number of years, where we can now do direct exchange force detection and image things like spin spirals. And Dania more recently has been also being able to look at light emission from individual molecules. And so we try to use these methods to study what we think are interesting scientific problems. So the approach, which I've tried to already outline, is based on scanning tunneling microscopy. And we have a belief in our group that it's a powerful method because when combined with being able to image, for example, not just structure, but also getting at things like electronic properties or magnetic properties, and combining that with bottom-up control or clean synthesis, one can really start to tune materials and try to take complex problems. Magnetism is a great example of a complex problem where you have many competing interactions or degrees of freedom, and then being able to, for example, modify some of these degrees of freedom, one can hope to understand some things in a bit deeper way. This is a picture of our lab. So today I'm going to mainly talk about work actually coming from all of these different labs. We work, this is really, helium type research. We're really proud of our system that works down now to just 30 millikelvin temperature. We can gain spin resolution of materials. We can apply magnetic fields. And we're usually working in temperature ranges between 4 Kelvin and around 30 millikelvin. So I won't refer to temperature so often in the talk. In a few places I will, but this is really low temperature research and not room temperature research. I want to highlight the people that put in the hard time to do this stuff today. I want to mainly mention these 4 people. Brian Corrali, who's a postdoc, is about to start his own group in England. Elsa Knoll and Vanna, who are both PhD students in the group, and Umut, who was a PhD student who just finished his PhD last month. And this work was done in collaboration with a number of people, mainly with Misha Katznelson's group and Sasha Rudenko, who are actually locally here, and with the Donder Center under Bert Kapp and his master's student, Alec Kolmes. I will show a couple of results from some friends of Angela and myself from Uppsala, working together with Ola Eriksson, Anders Bergman, and a few other people. So let's start out with some physics here. I think this is a fun physics question because it's pretty far out. So, can we harness the computational functionality of the brain, but without the fuss, right? So what does that kind of abstractly mean? There are ideas when we talk about brain computing that are like, okay, memory, there are concepts of like plasticity. This probably even feels a bit biological, but the main one is, let's say, pattern recognition. But of course, we would want to be able to do that, let's say, in a solid state material, ultimately down the scale of, let's say, individual atoms. And we want to do all that stuff without all the fuss. And the fuss would be, we don't want to have, let's say, our computer chip be depressed or in love, or deal with the, let's say, more complex psychological aspects of what a brain does. So here we talk about a very rudimentary picture of what we mean by brain computing. So in traditional computing, if we talk about memory, we talk about storing in a computer every last piece of data, and it should remember everything to the very last bit. When we talk about our own memories, or talk about mine, if I was to introduce a picture, you kind of forget the details, right? And then there's some aspect of the picture that you may remember. And later somebody may show you this aspect of the picture, like in this case, the sun in the picture, and then you're able to recall the picture. This is a very, very different notion of memory if we just look at the contrast between, for example, how a computer remembers something and compare that to how we may remember something. So another more concrete example of that could just be shown by these images of 2 very famous physicists, Einstein and Bardeen. And so here I have just a black and white picture of these 2, and I help you associate these pictures. And now if I distort the picture, you're very easily able to actually recognize up to some amount of noise in this picture, what these originally associated patterns are. And so if we now translate this a bit more to a physics problem, we start to get at the root of one of the difficulties and why this is so fascinating, is because we really talk about 2 different worlds. In one case, we really talk about bistability. We talk about large energy barriers and bistability, and these are things we associate with things like ferromagnets. But in these kind of contexts, we really start to talk about multi-well landscapes and dynamics. So how do we picture that? So if I have a simple cartoon, and I was to say, going back to this Einstein and Bardeen example, we would call, in neuroscience, people would call the local minima of some energy landscape an attractor. So here I label that A1 and A2. And the idea would be that the information that is related to these 2 different pictures is stored in this local minima. And the idea of recognition is then labeled in the physics problem, in which you say, okay, if I show a distorted part of this picture, I end up somewhere within the phase boundary, but with the onset of dynamics, I'll somehow attract back into this local minima, and then I'll be able to recall this individual pattern. In the same case for the Bardeen case. And so for that, if we say, how do we actually be able to realize that in an actual material? We would need some kind of energy landscape that is inherently tunable. So we want to be able to remember any kind of picture. We don't want to think about Bardeen and Einstein, or at least I don't want to. And you need it to be sufficiently complex. You need to have many, many minima so you can also remember a lot of things. So if these phase boundaries or these humps in the energy barrier are sufficiently large, you would never be able to attract to any different part of the energy landscape. So they have to be also relatively flat. If we foreshadow what people had theorized in neuroscience, so for example, this is reminiscent of the Hopfield problem. The actual idea is that the local minima, the magnetic metastable magnetic ground state, if these are now Ising spins, so the idea that down and up are bright and dark, is that your minima is the actual picture. So any of you that work in magnetism may know it's pretty difficult to create a complex magnetic state where you actually have a picture of somebody. Usually things want to just be ferromagnetic or antiferromagnetic or paramagnetic and thus very noisy. And so this is inherent, the difficulty of the neural problem, and trying to now translate that and say, for example, in a spin network, how could I actually make a spin network do something brain-like? So I find this fascinating. There are a lot of people in this world today doing great things with this picture. This is also painting the brush of the world people call neuromorphic engineering, where people are now making chips that mimic neurons and synapses, and I'm going to come back to what that means to later. But in physics, it's also really fun, and I would say often not well understood regime in physics, where we talk about multiplicity. We talk about landscapes that are something in between what we would imagine for something like a ferromagnet or any kind of bistable system, and all the way to the other limit we call glassy, where we have uncountable number of minima in a system, and there's enough temperature that the thing is just fluctuating all the time. And in this limit in between, where we would like to have something like neural complexity, we talk about systems that have multiple energy minima and some kind of more complex texture, but fall in between these two different pictures. And the physics associated with that, the spin dynamics, the energetics in those kind of pictures is in itself leaves a lot to explore. So that's kind of that picture. And I would say quantum materials, right? So that's obviously a buzzword. I think that's how a lot of the condensed matter people phrase materials these days. And since I've been doing physics, it's all been about trying to find better paradigms for information technology and sensing, whether it's been in spintronics or trying to also manipulate the quantum degrees of freedom. And how you actually uniquely do this, I just showed a simple example with magnetic order, but there's tons of different things that are out there. So in the 20th century, right around when I started doing physics, the main things we were excited about were, semiconductors and its tunability and ferromagnets. And if we jump ahead today with the whole zoo of things that we have out there, we come to many, many more phenomena. The reason I mentioned that, I forgot to mention the step here, is that this idea of having tunability has mainly been about computer architecture. It's been in this picture of von Neumann. So the idea that I have a processor where I process information, I shuttle that back and forth to a storage unit, so it can be a short-term storage or a long-term storage. And the idea is then to make very fast switches and make robust storage devices has been to fit in this paradigm. If we look at the quantum materials we have today, I can make lists that's I could probably spend the whole talk just making these lists, but we have so many, many more phenomena that we can control, ranging from not only just tunable conductivities, but there's topology now, entanglement, coherence, many complex magnetic states, so skyrmions or non-collinear magnetism. We can work in non-equilibrium, access states of matter that don't exist in equilibrium, all sorts of many-body ground states, charge, spin texturing, superconductivity, ferroelectric behavior, and much, much more. And so there's a whole kitchen full of complex phenomena we can turn to. I'm only going to talk about a very, very small subset of all this, but it's an exciting time to now ask, hey, can we take all of these different kinds of phenomena that we have out there and now do something a little bit different than this old kind of von Neumann picture where we're trying to just make a better transistor or a better double well potential. People have done that. So magnets have been a fun place to do that. So a research I've been involved with for a very long time is the ability to create a single atom magnet. People have shown that you can use symmetry and magnetic anisotropy and actually scale down hysteretic behavior all the way to a single atom. So this is some work pioneered by Radboud and co-workers in Switzerland, and here's some work from Fabian Nataga and a group in IBM, where they can now use the scanning probe microscope and actually detect the stochastic switching of an individual atom. I show this particular picture here because this is already reminiscent of something we would call a neuron, which I'll highlight a little bit later. But again, just to highlight the zoo, this is another fun picture I found showing that there's endless amounts of these different kinds of interactions we can interface with. So quantum computing is a different world, and I don't want to spend much time talking about quantum computing in principle. But I think that when I start thinking about more and more neuromorphics, and we talk about working about brain-like functions down to an atom scale, we also can open up new functionality and start thinking about how can we also use concepts like coherence and entanglement also in pattern recognition. And so I wanted to show that slide just for the sake of completeness. But in this kind of simple picture, the architecture is mainly based on, let's say, manipulations of the wave function, for example, on a Bloch sphere. So when we put all these different kinds of architectures that are out there today, we go from the simple computing architecture that we have, separation of processing and memory. A lot of people are working in quantum computing. And the part I want to focus on today is mainly about machine learning and this neuromorphic concept. So there we really talk about, as I showed you in that picture of the multi-wells, and I showed you in this picture of Einstein and Bardeen, we need to be able to tailor complexity in materials, gaining multi-value states, multi-well potentials, and starting seeing what kind of emergent or complex behavior comes out of this as we build it bottom up. And I tried to inspire these different architectures by these simplistic real life experiences. And I think the neuromorphic one's well encapsulated by this church in Barcelona, the Gaudi church, which I don't know if will ever be finished. So let's move now to what we're actually doing and how we're going to do this. So what are the specific hardware specifics we need, and what are some of the ingredients? So machine learning is the ultimate spherical cow approximation. If we talk about that picture I showed you in the beginning of a brain, and we say, okay, we want to make a material brain-like without all the fuss, we talk about a simplistic reduction in which we just create algorithms. And in these algorithms, we say, I have an input, I have an output, there's some kind of functionality. And now the idea of neurons and synapses are elements in this algorithm. We're no longer talking about higher type brain-like functionality or biological units. And so that's kind of the model that we work in. And the inspiration for a lot of these neuromorphic concepts is coming from the analogy that machine learning is a good description of these computational problems. In the field, what a lot of people do is they take machine learning, they take a specific machine learning model. Many of you are probably familiar with some of them that are out there. They then piecewise design different types of circuitry. So they'll take the most famous example is that of the so-called memristor, and pattern different kinds of memristors together. And then from that, they'll derive functionality, and they'll utilize things like computers to implement learning. And I think this combination of, okay, I make a chip, it behaves somehow, does multi-valued functionality, I siphon it and I train it with a computer, is certainly not long-term the ultimate goal, even though it's very beautiful. Many of the examples people are already producing on chip at room temperature. And these are some of those bottlenecks, and that was the inspiration of the things I'm going to now talk to you about. If you start saying, can I make a material itself that's self-adaptive? Can it learn by itself? Or can I utilize concepts like quantum that may actually induce new functionalities we haven't envisioned? Or envelop all these things in one material instead of taking sequential kind of series pieces of materials? These are a lot of the interesting physics questions that are still out there and beg still a lot of new understanding. So that was a long-winded description of, let's say, some of the motivation of why I've been interested, particularly in this kind of picture, and how we can now ask questions about what do quantum materials do? How does this give us maybe functionality like machine learning or maybe more? And what can we do with that? In the meantime, how is that linked to real physics problems such as interactions, multiple timescales, multi-wells? So today's presentation, I'm going to now show you three pieces of that. I'm going to first talk to you about a system that we developed where we discovered a new type of spin glass state and why these multimodal landscapes can be understood in terms of spin glass physics in a limit. And then I'm going to turn to another model system where we actually have done this bottom up with individual atoms. And that's based on a new concept of memory. So a bistable unit we call orbital memory, which is realized from an individual cobalt atom on the surface of black phosphorus. And then I'm going to finally show you that when we couple these circuits, we can actually realize these machine learning analogies in one material system to the atomic length scale of what neurons and synapses are like. So the Boltzmann machine will be the background of what I talk to you about from here on out, but it's good to revisit this Ising model. So if we look at the Ising model in detail, we talk about the Boltzmann machine. This is actually very familiar to a lot of physicists. This is nothing more than an interacting spin model, where if I replace W here with J, I would call that the exchange interaction, and I have my binary bits. And then this is some kind of effective Zeeman field that acts on each of the individual spins. In a machine learning problem, such as the Boltzmann machine, the S's now are what we call neurons, and they can be 0 or 1, but they fluctuate stochastically. So actually the states of the zeros and of the spins are always fluctuating. And the way they fluctuate together is now conditioned on these weights, on these interactions. So depending on what the value of double is, they may tend to fire together in a correlated manner or not. And so what does that give you? If we just consider two spins, so you would imagine that if my two spins are firing and I measure a steady state distribution of how they've flipped over time, I may end up with distribution 1. So where, for example, they're firing in a down state together, an up state or something in between, or distribution 2 here. And if we already kind of foreshadow our knowledge of magnetism, typically these distributions are bimodal, right? So states either want to be ferromagnetic, so they're always in the 0 or the 1 state, and they never populate something in between, or vice versa. But in the case of doing something neural-like and needing complexity, we want to be able to create many different kinds of distributions. And that's what's shown here in this picture. So if I'm firing, in essence, the machine learning problem is to create a system where I have firing neurons. So here I have spin 5 and spin 2, and they're firing. I hope this comes through virtually. And now if I measure that steady state distribution, I get this one. And then based on a learning problem, I want to now modify the interactions between these spins. So that's this kind of synaptic weight W. And by then modifying that weight, now you can see them hopefully blinking together. And now I modify this distribution. So the machine learning problem becomes not only about creating in a material something that would stochastically flip, but somehow I can now change how they're stochastically flipping with each other based on some memory element that's in the material that allows me to create this distribution. So if you're trying to learn patterns, that'd be something like saying, I'm going to now associate things like Swiss cheese or the Swiss flag. And I want to associate that now with one kind of distribution. And then I would draw a classification line in a machine learning problem and say, then this belongs to this distribution, whereas things like Gouda cheese and, which I could represent, for example, with a Dutch type of cheese would be a different distribution. And now you would want to be able to program these different kinds of distributions and classify this in a certain kind of way. So that's in essence what you want a material to do. And now we want to be able to create that in these two distributions, for example. So then if you input into the system something like a cheese, like this would be now an example of fondue, you would argue, okay, now my system would collapse into this particular distribution and recognize that analogous to that multi-well potential I showed you before. So for the Boltzmann machine, we started asking ourselves, can we realize this with arrays of spins? So one of those ingredients is to now create magnetic interactions that are long range. So magnetism, the most familiar type would be the RKKY type interaction, which has the sinusoidal oscillation. And here you can see an Ising array now of 25 by 25 spins. And what's color coded down here is the interaction. So here, I'm mainly now coupling all of my neighbors with one sign type. So that's now positive. So this would be like my ferromagnetic analog. And what I now change as I move across these pictures is how much that RKKY interaction is beating. And so what you see now is that there's a long range coupling character. So the one in the center, its furthest neighbors, it still sees ferromagnetic. Now it sees something anti-ferromagnetic and then something ferromagnetic. And now you can modulate this and increase this kind of beating frequency. And one of the punchlines that I'm going to come out and tell you is that by increasing these competing interactions, you also start changing and sculpting the shape of these energy landscapes. So this is a hypothesis that Bert Kopp and Misha Katznelson and our student Alex Kolmus we had at that time was saying, if I can actually make a spin array and couple the system and start competing the interactions, I should start being able to tune myself into these more complex landscapes, but without any kind of disorder in the system. So that's one of the messages to impart from that. And how do I look at that physically? So this is a very deep but instructive picture. So this is now my state distribution. So these are my density of states, and this is energy. And if I go from a system where I have the picture that I showed you on the left, I have a bimodal distribution. Here's my big energy barrier. And as I now start competing interactions, I start getting a smaller and smaller variance of the states until I start clustering all the states around each other. And what we want to be able to do things that are more, let's say, brain-like or interesting is to create energy landscapes or spin analogous landscapes where we can get something in between here, where I have some sufficient complexity in my landscape, but they're not too noisy. We started studying the magnetism of these surface of these patterns, and you can then go back to this picture here I show you and say, what's my expectation value of my spin in these Ising arrays? If I look at these low energy states, this is the obvious case, this is the ferromagnet. But let's say I'm over here and I start looking at these low energy states, what kind of patterns do I get? And it's fun. You can see here, like this is the all one sign character, my ferromagnet, my double well. But as these landscapes start getting competing and sufficiently complex, there starts to become symmetry breaking in these patterns. These low energy states start favoring. Here you can see something that looks like QR code. You start getting more smeared out patterns until you even ultimately get to what we call the Pac-Man state. And you start getting many, many states where they're very, very similar in energy, and they all favor kind of slightly different local distributions. So how do we make these different kinds of states? And at that time when we were theorizing this stuff, in our lab, we were studying a material called neodymium, and we had found this state. And you could ask yourself, why is this so difficult to imagine in magnetism? And as I've shown you before, we can make magnetic memory in single atoms. We've shown this. We've also shown this earlier for larger clusters of iron. So these are 5 iron atoms. We can create things that are stochastic and behave like neurons. You can do this down to the single atom level. So we can make an Ising spin, and you can interact them. This is some work that I had performed in Hamburg and Wiesenanger's group. This is work from Sebastian Loth and co-workers at IBM Almudena. This is more recent work from Wiesenanger's group and some work from Sander Otte. And the moral of the story is you can also create RKKY couplings. That's actually shown in this top left picture here. And you can tune the distance between these Ising spins. You can get an antiferromagnetic landscape. So why isn't this just going to work for something neural-like? And the reason is it has to do with the nature of the exchange interaction. Exchange interactions are very, very local. The nearest neighbor interactions are very, very dominant. And if one wants to build something more in this complex landscape, if I stare at this picture of this chain, I really need the ends of these spins to also talk to each other with some amount of strength that's equivalent to the ones that are next to it. And that's why that's so difficult. It's really to create in the magnetic system these energy landscapes where you have this kind of stronger connectivity between all the different spins. And that was kind of what I tried to show you in that Ising example, where you have kind of a 2D grid of things interacting. And so we had found our first material to do that, and that was this discovery of the spin Q glass. And this we had done together also with Olle Eriksson's group, with many of his colleagues there, Anders Bergman and many others. And we had studied this elemental neodymium. And at that time, there was a fun puzzle, which is that people couldn't really figure out what the magnetic ground state of this element was. They knew that there was a purported Néel temperature. So there was some kind of claim that there was an anti-ferromagnetic type of ordering. But in the system, they found that as they cooled it down, it never really chose one type of ground state. And we utilized the spin resolved imaging technique, and that's highlighted in this picture here, to look at this magnetic ground state. So this is the surface of bulk neodymium. Here you can see a size scale that's 50 nanometers, and up is bright and dark is down. And if you stare at this for a few minutes, you see that the system shows local order. So they're like these little platelets here, or if I now kind of move to the right, you see there's stripes, but then the periodicity of the stripes start changing. Like here, for example, it's different than here. And the system actually has a tendency to want to form an ordered spin state locally. And these are frozen. So we measure these over a very long period of time. But the system doesn't choose one state, right? So this is not long range ordered. So there's actually many, many favorable configurations. And this is already now reminiscent of this picture I showed you, where each of these different magnetic patterns can be equivalent to one of the multiple minima in the system. So this was already exciting for us. We were at the same time thinking about a very different problem, this neural problem, and already realized that this picture of neodymium, if you blur your vision a little bit, has something already reminiscent of these kind of very, very complex low energy patterns that we would already observe in a simple Ising model calculation when we put in a lot of competing interactions. And so Anders and Ole Eriksson and their colleagues, they also looked at this from a first principles perspective, asking how can we get this landscape out of the system? And it's still really a puzzle why, but we found out that based on this crystal structure, this DHCP crystal structure of neodymium, this is now the exchange interaction, and this is now the distance. And what you see is that the prototypical 4F material, by the way, for those people well in tune with magnetism, you get for an HCP structure, you get your RKKY-like interaction. But now because of this DHCP structure, we get lots of competing interactions down here. So the system, whether you go up or to the left or to the right, mainly want to always couple opposite in sign to its neighbors. And this creates lots of, let's say, entropy in the system, and now creates lots of competing or frustrated configurations that now the spins want to take. We were excited about that, and we thought, hey, isn't this already something to do with something brain-like? But unfortunately, or fortunately, depending on what your perspective is, the system still showed something attributed to spin glasses, which is it's a little too noisy. So here, this is the concept of aging in the system, where after we've perturbed the system, you can see that these local patterns, like here you can see fine patterns here with big checkerboards, but now it disappears. The system is still kind of aging and not really relaxing into one fixed state. And therefore, it still has too many wells compared to the absolute temperature to be able to use it and stabilize something like a memory. So in other words, different regions of this material could be used as a memory if you figured out how to get something in and out of it, which we don't know how to do, but it's too forgetful. And that's something that spin glasses, they do, and why people for a long time had realized that spin glasses are not a solution to neural problems. So this aging picture, I always show people a jar of honey. It's the same idea that your jar of honey over time, crystallizes. It's the idea that it never fully relaxes, but it's continually evolving. That's the spin analog, what's happening in these glass systems. So I'm going to go into the second and third part of my talk now. We asked ourselves, can we approach this differently? Can we actually make an atomic system analogous to these spin systems I showed you, but where we can stable now this multiplicity rather than these strong bistable ground states? And that was based on this concept of orbital memory we recently discovered in 2008. And we had studied that on the surface of black phosphorus. So just for a minute, I want to tell you what black phosphorus is. It's a van der Waals crystal, like graphite. You can basically Scotch tape cleave it, and you have these layers that are separated, and you have this buckled structure of graphite, of black phosphorus, excuse me. And what's really cool and special about black phosphorus and this kind of whole world of van der Waals materials is that it's very anisotropic. So it's a semiconductor. It has a band gap of about 0.3 eV, and it's pretty free electron-like. But if you look in one of the K directions versus the other, the effective mass is strongly different. And this has a number of consequences on its behavior, which we're able to actually utilize to mimic synapses in neurons. So how do you do this in an experiment? You just peel off some black phosphorus with Scotch tape in a vacuum chamber. The rest of the studies I'm going to show you now, those ones I showed you before, were done between a Kelvin and millikelvin temperatures. These were done around 4 Kelvin. You can do this in a standard STM setup. And when you put in black phosphorus, it's beautiful. You get these beautiful flat interfaces. Here you can see the buckled structure of these rows of the black phosphorus. And you can use the spectroscopic capability of STM and measure. Here you can see this is the valence band edge. This is the conduction band edge. You get these nice band gaps of the bulk, which are about 300 MeV in energy. And you can see that our 0 point is close to the valence band edge, so these systems are intrinsically p-doped. So why is this system anisotropic? You can do a very simple experiment. which is you can spray alkalis on the surface. And these alkalis, they have always one valence s electron. So to make them happy, they would just be happy to delocalize that electron and give it to the black phosphorus and then become ions. And if you give the system enough kinetic energy, then you have a bunch of ions, so basically that can sample the Coulomb interaction and measure out the dielectric screening of the material. And with that, you dope the surface. So if you put potassium on the surface, what do you get? You see that you dope the surface. So here you can see that the Fermi energy is now moved close to the conduction band. So that means that with potassium on the surface, it's donated this charge and made this thing N-type. And now that complicated bit I just mentioned to you, you can see a lot better in a picture. So here you see all of these potassium ions on the surface. This is now deposited cold at 4 Kelvin. And now you can heat the surface and give these potassium ions some kinetic energy. And what happens if they start interacting, you start seeing that they form these chains. So this is at 5 Kelvin, and now 8 Kelvin, and now at 14 Kelvin. They form these 1D structures. And it's fun because the rows of the black phosphorus are actually vertical. So actually, it doesn't even care about these diffusion barriers of the crystal. They feel such a strong Coulomb interaction mediated through this crystal. And why is this important? It's anisotropic. So it's actually easier to order in one direction than in another. So here the chains get a bit closer in this direction than, for example, in this direction. And it shows that the dielectric screening in the material is different in these two different directions. And that's what we mean when we say black phosphorus is an anisotropic semiconductor. So using this as a platform without potassium on it, we wanted to understand spins. So we decided to just sprinkle cobalt on it. And if you deposit cobalt on the surface, they look like what we now start calling goldfish. So here you can see these kind of structures where you have a lot of intensity in one spot, and then you have this feature that's related to the charge density. So the material, there's some amount of coupling of these cobalt atoms to the surface, but there's not perfect screening. It's not a metal. So you can actually see these charge densities of these atoms smear out across part of the lattice, and you can identify it. And one of the astounding findings that we found is that if we stare at one of these kind of goldfish states, you can see that here, if we applied a high enough voltage when we imaged it, it flipped and it turned into something that we now call a mushroom or a squid state. And we spent a long time with Misha Katznelson's group trying to understand what that was. And what we found is that these reversible pulses, the atom is staying in its same spot, but it's actually changing its orbital character. So we started to call this an orbital memory or an orbital switch. So here's an example of that, or here's a picture of that. And the way we can understand what's going on in this picture is no longer is this that I'm flipping the spin. So it's not that I'm taking the magnetic moment and changing its orientation from up or down, but I'm actually repopulating the electrons from, for example, the 4s to the 3d state and changing the balance. So I'm not charging the atom, I'm just redistributing the charge through its different orbital configurations. And since they all have different behavior and interactions with the substrate, this leads also to a small relaxation. And this also can change the height. So it's a little bit more of a complex system, but the way of thinking about it is that it's a high spin and a low spin system. And we can now electrically change that magnetic moment with a pulse. So this is kind of the crude cartoon I always show around, that we can now change the different orbital configurations of the system. And this is a long-lived memory. So we can leave it in the 0 state or the 1 state. And this basically stays that way unless we apply a high enough voltage pulse, and then it can flip. And what we found, which makes this now neural-like, is that if we apply a large enough voltage, it starts to stochastically flip. So this is just a cartoon of that. You can think of the tip as basically locally gating this atom, and then it induces these stochastic fluctuations, which would be the S element of that Boltzmann machine. And so here's just an actual data representation of that. Here, if we measure this at a given voltage, we can tune these different lifetimes, and we see a stochastic flipping, which we can image in its frozen state between one of these two orbital memory states. So we have something very similar to the spin behavior people have studied for single atoms, but now this is kind of on the orbital degree of freedom. Each of those orbits has spin. We haven't probed that here, but this is now an all electrical readout. And now I want to show you something what we still think very magical about the system that happened when we started coupling them. So if I go back to this Boltzmann picture and kind of one of the punchlines of my talk, The idea is to create complexity, create multi-well landscapes. And we need to now be able to, for example, couple two spins, and we need to be able to create this weighted structure and create multiple stable configurations. And Edsa, she had spent quite a bit of time during her PhD figuring out how to move atoms on black phosphorus. And here you see two of these kind of fish structures I showed you earlier. And it's strange when you study the stochastic behavior of it, you see in the spin in the current noise, you see now 4 states. So if this thing is acting like a ferromagnet or an antiferromagnet analogously, or wants to couple in such a way, you'd imagine that this thing would flip from an up-up state to a down-down state. But what we're seeing in this kind of noise is that it wants to be in a down-down state, and sometimes it wants to be down-up, or up-down, or up-up. And there's actually a finite distribution of these, and you can measure this then for long periods of time and create a distribution very similar to that Boltzmann distribution I showed you earlier on, and get 4 possible states. And as you scale this, this is again reminiscent of creating now a multi-well. And as you scale this up, so for STM people, scaling it up means now just 3. You put 3 of them together, now you get more states. So you start seeing more and more complexity in the switching. And we found regimes now where we can even get these distributions to show all of these different 8 configurations. So that means that there's actually not a double kind of barrier picture where I have 2, ground states that are favorable and lots of excited states, but now I have kind of a landscape where I'm able to populate the residency of all these different lifetimes. And it's surprising on these distances are on the order of a few nanometers. And so this is speaking to some kind of electrostatic origin. It doesn't really depend on the distances. So here I just show you different distances and different configurations and just snapshots of that noise. And you can see you just get all sorts of complex distributions of the state noise. So it's not just one unique configuration in one specific part of parameter space. We get this almost all the time when we're in a certain region. So it's very insensitive, and this multi-well behavior is pretty robust. So you could actually argue you've already made a synapse, Alex. That's here my synapse determines this distribution, but that's a boring limit because that's now dictated by my substrate. And in order to change the distribution, I'd have to move the atoms around, and then the humans moving it around. And that's not something intrinsic to the material itself. And so how do we actually program that into a material? How can I get the black phosphorus to actually change its distribution itself? And that's the neural problem. And there we realized the first shot is to use this anisotropy of the substrate. So remember, the dielectric screening in one direction is stronger than the other. So now if I gate the structure and I put an orbital memory atom now in a vertical direction compared to horizontal, it'll effectively more weakly couple, for example, to the 2 atoms that are down here. And that's a really cool thing because here, now I can gate these 2 atoms, these 2 flip, this is stable. And then I can flip the state, compare what happened. And here's now the example of that. Here's just a snapshot of the noise. So here you see 4-state noise. These 2 are flipping between the 4 different configurations. And now if I flip this atom, which doesn't flip, I get a different distribution. And if I measure the steady state distributions, indeed they're different. And now this is the smallest example. By far, it's the most trivial example, but of where I have now 2 neurons and 1 synapse in a circuit here that's now based on this kind of multiplicity of this system. That's really exciting. And so this kind of what we now call the K state, and that's this atom above here, behaves in a synaptic way and now conditions the distribution of these 2 atoms in this so-called circuit. And you can then start modeling that. That's something we now did with Bert Koppen. So he's our resonance machine learning expert. And then you can actually mimic this physical system where I have these kind of complex couplings and now try to model the different stochastic behavior of these spins interlinked with local biasing fields and an overall synaptic weight. Now, this is a 2-state neuron. So you only get, a 2-state synapse. So you only get 2 values of your weights. You can store 2 distributions. How do you make that more complicated? You can just introduce more neurons. So here's, again, the 3 neuron picture. And now you can put 4 atoms around it. And you can switch all the different configurations. And you start seeing that the stochastic noise just becomes very, very different in all the different cases. And you can start now storing many, many more different complex distributions. So in this way, you can actually mimic a Boltzmann machine. This is a really beautiful and elegant example of how you can now take up a bottom-up picture. And of course, the puzzle remains, why does this system behave this way? Can I now start relating these fundamental interactions between the changes in orbital population, the relaxation of these systems, and understanding how this leads to this complex physics. I just want to conclude on an exciting point. I'll skip the Boltzmann modeling and just mention a last point, which is that in this picture I showed you, and that's in this complex picture, these three are fluctuating, and these four on the outside, they stay stable. But how do I get this thing to also maybe potentiate itself? How can it learn by itself? Well, in the end, then you want the synapses to at some point also create another multi-well landscape in its own dynamics. And this concept of long-term potentiation is something we had heard about in biological systems. And this is the onset of adaptation in a material. So the physics would be, can I separate timescales? So I have something compute, it's really, really fast. That would be the horizontal spins. And then I have synapses, they start fluctuating, but very, very slow, and they're well separated in time. And we saw the ingredients of that in this system. If you apply certain kinds of electric fields, you can see that these three fluctuate. That's what's shown here. And then in a much longer time period, and I just zoom in here, you see that actually one of these K states fluctuate. And now you get a very, very different distribution because one of the synaptic states has changed. And we asked ourselves, can this now be analogous to adaptation or self-adaptation and the onset of having this thing start learn itself? And there the idea is you have a stimulus, the synapses change their behavior and condition the different neural states. And in this particular system, why does it change? We realized it changed because the system started to recognize or adapt its, let's say it starts to adapt its dynamics based on an input voltage. And so this is a much more complex histogram. These histograms down here are the distributions that I showed you before. And now I start showing you a distribution and measuring for a much, much longer time, so thousands times longer. Now these K states, now that they slowly start fluctuating, and you start seeing that the distributions they take start also changing depending in condition on the input voltage that's there. So with that, I want to conclude my talk now and mention that I tried to take you through a little bit of a landscape of going from this abstract notion of, can we make materials behave a bit brain-like, and introduced some of the basic physical principles that we would need. So the idea of creating multiplicity and energy landscapes. I gave a tidbit of spin glasses in there. And then I showed you a bottom-up system where we can now strive to understand and link much more intricately the physics of multiplicity to machine learning in these systems. And I think there's lots of fun directions we can go into. And I just want to highlight a few of them. We're pretty excited about, for example, understanding how the spins actually behave in these orbits, and also developing a lot of the new theory to understand why we get this complexity or this kind of built-in glassy behavior in these atomic networks. With that being said, I'd like to thank you all for your time. And I guess, yeah, I'll turn my over to Angela. Thank you.
Thank you, Alex, for the wonderful talk. And I ask everyone to open your microphones to give a hand to Alex. Thank you. I think I have to leave the thank you a lot. So questions, please. You can raise your hand, or I would start. So it's really quite interesting, this orbital memory. So you have tried one type of substrate, and would it be interesting to have different types of substrates, and like Misha has a kind of Hamiltonian where the orbital-orbital interaction would show up, and then you can have different, not only zeros and ones, or even other states, like, I don't know, frustrated states, like in a triangle, this and that. Would it be interesting to this kind of Boltzmann machine or something like that, or not?
Absolutely. So Misha actually, with Sasha Rudenko, their first prediction for this kind of So orbital memory, maybe a more appropriate term for magnetism would be, multi-stable valency. And they found multi-stable valencies for cobalt on graphene. They found 4 states, actually. I'm not aware of anybody that's seen that on graphene. For us, it's a lot harder to change the substrate than to change the atom. So we're actually trying to now see if other atoms on black phosphorus show that. That's one of our objectives. Long-term, we should look in more systems. 4 states you can try to predict probably from these different kinds of models you mentioned. Where I would probably go in a direction that's easier is to say, if we have weak spin orbit coupling, the spin is also there. And then depending on the magnetic field and the electric field, there may also be multiple degrees of freedom, just kind of unraveling the magnetic moment now. And so we're interested exactly in these kind of questions. If you also have, it's strange to think about it, but if you have another orbital memory type that has a different time scale and a different moment, if you also go heterogeneous and you just say, let me take cobalt and then another orbital memory type, you also get, again, all sorts of complexity. And so I think there are all these different directions. There's different substrates, there's different atoms. Even on the same substrate, you can couple different atoms. And then these different interactions, like you probably well know, I'll just stop on that point. The exchange interaction now will be conditioned on the orbital state. And so if you now start changing one of the orbital states, the way they even couple magnetically will change. And so you could also start engineering frustration that way. So there's lots of directions to take. I find this idea of multiplicity fascinating, and it's exhausting how many different directions you can actually go into. Yeah.
Yeah, I can imagine. And I don't see another question. Another question I have that comes from chat. So concerning the challenger for the experimental point of view concerning the learning time depth and behavior, what do you consider what is the most difficult thing from the experimental point of view to go through deep on this research?
Yeah, so like this, we've batted this around a lot. So I do have a prepared answer for this one. I mean, the STM is the bottleneck here. I mean, it's cool that you can do this atom stuff, but at some point one would want to scale this to a bigger device. The orbital memory concept, I think it requires a surface, but it doesn't require an STM. One could think about backgating this and trying to drive it that way. So it would be nice to understand how big this can get, how these couplings behave. So that's just talking about a device. Now, if we talk about learning, there also is a big question about, okay, I have this, let's say if this was big enough, a Monte Carlo sampler, right? How do you get your stuff in and out of this thing, right? Is it just reading the current? And then, so how would you input patterns? So would you get patterns out? So, I mean, these are really, if you ask me, like 20-year kind of questions, right? This is really not something we can do in a year. And then if one wants to start breaching these other questions like spin, is there actually possible entanglement in the system? Then these also become questions about timescales, and can you actually access faster timescales and not slower ones? And so I think there are enough puzzles there to, for me to keep me busy for a while. But it's challenging. So the orbital memory platform, to make it useful, has a ton of challenges that are material fabrication based. I think in terms of understanding, can you build a spin glass and stuff like that? I think at some point the STM becomes a bottleneck. So we can still learn a lot, but I think there's still lots of directions to go into that leave the STM. Yeah. Okay.
Thanks, Alex. I have some congratulations from researchers like Julio Krasinski from Sirius. Is a huge accelerator here in Brazil. It's impressive, your talk, but he had to leave. And now I stop sharing from